In this video, we are going to learn how to write a trigonometric expression as an algebraic expression. So for each of these examples, we'll write each trigonometric expression as an algebraic expression in u being the variable that's inside the expression right now. So one thing to keep in mind with this process is it's very similar to the first video in this section, but we're just using a variable, and also when we're using a tangent from this range, does it affect the output from the range of this function? So let's look at that. So first we have tangent inverse of u, which we know its output angle is going to be somewhere from negative pi over 2 to pi over 2, which is very similar to, which is the same as sine. Sine is both negative and positive in this region, so we should have no issue going through this problem. So first I'm going to draw a triangle. I like to just use the first quadrant as default, but you can draw it any way you'd like, because the angle could have also angled downward as well. But either way, up top we'll get a positive sign, down below we'll get a negative sign, but it'll be covered with the u, whatever we use there. So tangent of u, tangent inverse of u can be rewritten as tangent of theta is equal to u, which could also be thought of as like u over 1. So tangent of theta will be opposite over adjacent, so u over 1. In our problem, we're looking for what is the value of secant or sine of theta, which would be opposite over hypotenuse. So I need to use Pythagorean theorem in order to find the hypotenuse side of my right triangle. So I'll have 1 squared plus u squared is equal to c squared. Solving for c, I'll get c is equal to the square roots of 1 plus u squared. And that paw you just saw was my cat Taki. So the hypotenuse is the square root of 1 plus u squared. So now sine would be u over the square root of 1 plus u squared. So this expression here, sine of tangent inverse of u, is equal to u over the square root of 1 plus u squared, which accounts for both the positive and negative values you might get with sine. So next we're going to look at tangent of cotangent inverse of u. So again, cotangent inverse uses values from 0 to pi, which from 0 to pi, tangent can hit all sorts of values, both positive and negative, so I don't have to worry about any sort of sign change. But I do have to be worried about at pi over 2, tangent is undefined. So I need to make sure in my expression that if I were to get pi over 2, it would count as undefined. So as I go through this, I'm going to draw my triangle. Again, cotangent of theta would be equal to u. You can also say u over 1, which would be adjacent over opposite, the reciprocal of tangent. And what's nice is I'm looking for tangent of theta, which would be opposite over adjacent, so I don't even have to find the hypotenuse for this problem. So I just have to put it as 1 over u. So my answer for a tangent of cotangent of inverse of u is going to be 1 over u. Now, the one thing I have to look out for, as I mentioned before, is tangent is undefined at pi over 2, and this expression is undefined at 0. So what would be cotangent inverse of 0? Now, lucky for us, cotangent inverse of 0 is pi over 2. So what's really nice is that this expression covers that situation for us that we would run into with tangent being undefined. So since this is already undefined at 0, this is the perfect expression to represent that trigonometric expression. So we are done with that problem. So as you see, the process is relatively simple. You just have to check to make sure your expression still matches what's possible for your expression. That's all. Let's try one more example. We'll have cosine of cosecant inverse of u. So what I know about cosecant inverse of u, I'm going to draw my right triangle to get ready, is that its output is from negative pi over 2 to pi over 2. What's really interesting here is that cosine is always positive along that output. So no matter what, my expression needs to always be positive. That's all I have to keep in mind. Here, following this, I know that cosecant of theta is going to be equal to u over 1. And I know cosecant is hypotenuse over opposite. It's the reciprocal of sine. Again, I can also write this as sine of theta is equal to 1 over u, and that'll also clear that up pretty quickly. So I have u as my hypotenuse, 1 as my opposite side, and now I'm looking for what is cosine of theta in this triangle, which means I need my adjacent side. So I'll have to use the Pythagorean theorem again, but this time it wouldn't be for c squared, it's going to be for b squared. So I'll have 1 squared plus b squared is equal to u squared. And I'm going to solve for b. So b squared equals u squared minus 1. And b is going to be equal to the square root of u squared minus 1. So with my adjacent side being u squared minus 1, cosine will be equal to u squared minus 1 over u. So my expression up top, cosine of cosecant inverse of u is equal to the square roots of u squared minus 1 over u. And now we'll come back to what I mentioned earlier, is I know cosine has to always be positive. This expression has the potential to be negative, not with the square root, because that can only be a positive number, but this u in the denominator. And the easy fix for that is just to put that u in absolute value. So now the expression is positive. So the answer for cosine of cosecant inverse of u is the square root of u squared minus 1 all over the absolute value of u. And that is how you write a trigonometric expression as an algebraic expression.